Thank you. Right, so Luke is right in that this would be, I think, the most traditional philosophy talk in this workshop, probably. And so that means, in particular, it's going to be kind of abstract to a large extent. But one of the things one of the sort of selfish reasons I want to give this talk to you guys is to try to connect it up in some ways with some real examples, and in particular from climate science, which I think is very relevant to the issues that I'll be talking about. I'll sort of mention some ways in which I think it is relevant, although really my confidence that it's relevant to any particular issue in climate science is much lower than my confidence that it's going to be relevant to some issue or other in climate science. So that's sort of one of the things I want to get out of this talk, is to get responses from you guys and how, if at all, this is relevant to issues that arise in climate science and communicating climate science to non-experts. The talk will also be kind of non-selfish or selfless in that I'm going to try to introduce some sort of prominent theories or prominent philosophical accounts of how philosophers have thought about how scientific theories get supported or confirmed by just regular empirical evidence. So I'm going to, so those of you who are not philosophers of science and are not very familiar with philosophy of science, you might get some sort of introduction to those sorts of issues, and so hopefully that will be interesting to those of you who don't already know those theories. So one way to introduce the issue that I'm going to be talking about is to note that I think it's commonly argued, or at least assumed, that the fact that scientists often disagree about some set of issues undermines their epistemic authority quite generally. And specifically, the fact that a group of scientific experts disagree on issues in their area of expertise is often taken as a reason not to trust those scientists, even on the things on which they do agree. So even on the things on which there's a consensus. So one possible or potential example of this would be the fact that there's a consensus on anthropogenic climate change. So the fact that the theory that climate change is largely, or to some extent, caused by humans. So that's I can take it to be a consensus on that. But there's a disagreement, of course, as we have seen in this workshop, on a lot of issues in climate science, other than that particular general claim. So, for example, one of the things that I understand that there's a significant disagreement about is whether, and if so, why there's kind of a pause in carbon dioxide-induced global warming. So whether the warming is a pause in the warming right now. And there are various other issues that we've been talking about in this conference on which there's disagreement. And still there's kind of consensus on this general claim that climate change is caused by humans, at least to a large extent. And often you see, for example, on blogs, and you see this sort of in the public debate in various ways. And I can give you some examples of this, but you often see the disagreement about these various other issues as kind of a reason to distrust scientists, even on the stuff in which there's consensus. So that's one example, or at least a possible example of what I'm going to be talking about. Another possible example is a report that was commissioned in 1956 on the probable amount of mutation induced by atomic radiation systems of the atomic age. And the US government had some atomic scientists, so radiation experts, produce this report about what the danger of atomic radiation would be, roughly. And they came out with this report on which they sort of had a consensus view on the probable amount of mutation induced by a specific amount of atomic radiation. But they disagreed on a host of other issues that are related to that issue, but they didn't really talk about that in the report, and they sort of so John Beatty, who's been studying this, who's an historian and philosopher of science, he sort of has written a paper on this where he sort of goes over how they sort of they sort of deliberately didn't talk about how they disagreed on these other stuff, because they thought, well, that's just going to kind of confuse the public and undermine our epistemic authority, even on this thing on which we are in agreement in this report. So that would be another example in which at least it looks like scientists are thinking that this is a way in which the public thinks. So, so what I'm going to be arguing is that actually not just that that's false, not just that that's a kind of a fallacy to argue that that's in that sort of way, but actually that the opposite is true. So I'm going to be arguing that the very fact that there's disagreement among scientific experts about various issues within a theoretical domain, so for example climate science or something like that, provides a positive, although pro tanto reason, for us to trust among the issues on which there's a consensus. So that Latin phrase pro tanto means that it's a real reason, but it's a reason that could be outweighed by another reason. So for example, the fact that Nick likes to smoke, he thinks it's a nice feeling when he puts the smoke up into his mouth or something like that. That's a real reason for him to smoke, although he has a much stronger countervailing reason for him not to smoke, which is that he's going to get lung cancer pretty soon. So it's a real reason, but it's a reason that could be outweighed. That's a pro tanto reason. Now, I think this might have important consequences for science communication. So, for example, I think this might suggest, and this is one of the issues that I want to get a little bit clear on today. I think this might suggest that I'm right, that climate scientists, for example, should not shy away from acknowledging scientific disagreements when they're communicating with lay people, so non-experts, who are assumed to be rational. It's going to be important that we're assuming them to be rational, which is, of course, maybe maybe an idealization that's sort of going too far. Anyway, so the basic idea of the argument that I want to give is that, so this is just the basic idea. I'm going to try to spell it out in various ways, but so the basic idea is that the fact that a group of scientific experts often disagree suggests that they wouldn't reach a consensus on an hypothesis, let's call it H, unless there really is strong evidence for the hypothesis H. So I'll explore three ways of fleshing out this basic idea, and this is where I'll sort of introduce these philosophical theories about how scientific theories are confirmed by empirical evidence. So an Bayesian approach uses something called Bayesian confirmation theory. An explanations approach appeals to something called inference to the best explanation. And finally, a robustness approach appeals to something called inferential robustness analysis. The two of those are going to be familiar to all the philosophers in the room. The third is going to be familiar to probably all the philosophers of science in the room. And Elizabeth Lloyd has written some really good papers on robustness analysis of pretty good kind. It's a sort of a more recent approach that's been taken in philosophy of science. So really what I'm going to be doing is just sort of flesh out this basic idea in these three different frameworks. I'm going to argue that you can do it in all three frameworks, and therefore there's a really good reason to think that this argument is a good argument to make, irrespective of which framework for thinking about these things you want to adopt. So before we get to that, I just have a few slides on sort of preliminary points and terminology. So our concern is going to be with what sort of lay people, that is to say non-experts, who don't have direct access to the relevant evidence, but they can conclude about whether the opinions of experts are epistemically justified. That is to say, well supported or warranted, or whatever word you want to use for that. Epistemically justified just means it's what they should believe, basically. For those of you who are not familiar with that term, by the evidence available to the experts. Now, one issue that I don't want to get into is that evidence can be misleading. You could have evidence for something, you could have the evidence pointing to something being true, but it's in fact false. Right? That's a possible situation to be. Hopefully that doesn't happen so often. But in that case, even a justified expert opinion would be wrong. That's just not going to be our concern. I'm going to try to bracket that issue here, and so I'm just going to be concerned with what the consensus and the disagreement together tell us about whether the expert opinion is justified, not whether it's true. So that's just to bracket this issue. And one thing I want to note is that the issue here isn't really about what scientists themselves should believe. So it's not really sort of coming up with prescriptions for what scientists should do, but really about what non-scientists should conclude from scientists' beliefs. So it's really about what sort of people standing outside of science should conclude from the opinions of scientists. Right? So what sort of, another way of putting the issue is like, what sort of testimonial evidence does expert disagreement provide regarding consensus theories? And so this is an issue that falls under social epistemology, if that tells you anything of science. Okay, so terminology, I just have some terms that it'll be convenient for me to introduce. So I'll use COM H1 to stand for the proposition that the scientific experts overwhelmingly agree that H1 is true. So for example, I think to be a possible example of this is a 97% agreement on anthropogenic climate change, assuming that's true. A disagreement will just mean, this term here, this H2 through Hn, would just mean that the scientific experts disagree on hypothesis H2 through Hn. So that's to say that they don't have a consensus on those hypotheses. And I'll just use just H1 to stand for the proposition that H1 is academically justified. That's to say warranted, well supported, whatever. Okay, so the first approach is called the Bayesian approach. I mean, those of you who are familiar with Bayesian statistics will sort of recognize a lot of the terminology, although philosophers think about sort of Bayesianism in a slightly different kind of way, I guess, from what some physicians think of it as holding. And these aren't really incompatible claims, it's just that they're sort of claims used for different purposes. So Bayesian confirmation theory says a few things. So one of the things it says is that rational agents, or perfectly rational agents, they have these fine-grained beliefs known as credences. And so this terminology has come up before in this workshop. So they're credences, or sometimes called subjective probabilities. And these are things that should satisfy the axioms of probability. So they should be probabilities in that sense. And these rational agents, according to Bayesian confirmation theory, should update their credences in a different kind of way, namely according to something called Bayesian conditionalization, which says that whenever you obtain any evidence E, you should set your credence in a theory, any theory, T, equal to the credence in T conditional on E that you had before you gained the evidence E. So basically, anytime you gain some new evidence, you replace your initial credence that you had in any given theory with the conditional theory, the conditional probability you had in the theory given the evidence. So that's known as Bayesian conditionalization. It follows from this that obtaining some evidence E increases the probability a rational agent assigns to a given theory, just in case this very simple inequality holds, meaning that the conditional probability of the theory given the evidence is greater than the probability of the theory. Right? Should be pretty intuitive. So according to, and then Bayesian confirmation theory makes a claim which says this is the way to think about what it is for a theory to be supported or confirmed by some evidence. So that is confirmed in the sense of incrementally confirmed, to be more confirmed than it was before. That's the idea. That's Bayesian confirmation theory, which is a philosophical theory about what sort of confirmation consists in. Now I'm going to try to put the question that I'm trying to answer in a Bayesian framework. And here the evidence and the theory are going to be not just a regular kind of theory and regular kind of empirical evidence, but the fact that there's consensus and the fact that there's disagreement is going to count as the evidence. And the theory is going to count as the claim that a given hypothesis is justified. Okay. Now, one thing to note, so to not get confused here, is that our concern is not going to be with whether consensus among scientific experts about some hypothesis H1 by itself confirms that H1 is justified. That's not really our concern. So our concern isn't with the kind of inequality and probability that's right here. Our concern is really with whether a disagreement about some other hypothesis, H2 through Hn, boosts the confirmation or increases the confirmation confirmed on the claim that that H1 is justified by the fact that there's a consensus in H1. So does the disagreement boost the confirmation, or does it just remain the same or even lower the confirmation? That's going to be our issue in a Bayesian framework. So this corresponds to the idea that the claim that H1 is justified is confirmed to a greater extent by the conjunction, or by the two claims that there's a consensus on H1 and the claim that there's a disagreement on H2 through Hn. So is that greater? Is a greater confirmation from that than by the consensus on H1 alone? So informally, the question then is whether this kind of inequality holds here. So notice that the only difference between what's on the right-hand side and the left-hand side with this inequality is the disagreement on H2 through Hn. The question is whether that holds, right? In the Bayesian framework, that's our issue. It turns out to be really very easy to prove that that inequality that I had before holds just in case this inequality holds. So basically that's to say that it holds just in case experts are more likely to disagree on H2 through Hn on these other hypotheses if they all agree that a justified theory is true than if they all agree that an unjustified theory is true. So I think all other things being equal, that is to say for kind of normal, reasonably looking agents, I think this condition is possibly satisfied. So after all, I think it's surely reasonable to assume that at least normally experts who have reached a consensus on an unjustified hypothesis would be more likely to reach a consensus on other hypotheses as well, because they have a lower bar for reaching a consensus. And so they're more likely to reach a consensus on other hypotheses, regardless of whether those hypotheses are justified. So that's really all we can say in a Bayesian framework, and because in a Bayesian framework we need to kind of assume that some probabilistic conditions like 4 hold, and so in some ways I think the Bayesian approach to this problem is the least satisfying, because we need to make an assumption like assumption number 4 in order to get our conclusion, which is this inequality number 3. And that's how things always go in a Bayesian framework. You need to have some probabilities to get some probabilities, and so that's in some ways it's the least satisfying, because I don't really have an argument apart from what I've just given you there, which is kind of a formal kind of argument for why we should think that condition number 4 holds. So in some ways I think the Bayesian approach is the least satisfying, and so that's partly why I want to consider other approaches as well. Okay. Now, so this is going to be the second of the 3 approaches. So I call this an explanationist approach because it uses something called inference to the best explanation. The basic idea behind this is another philosophical theory about how scientific theories get confirmed by evidence, or really any theory. Okay, so the idea here is that inferring some theory T from some evidence E, so T always stands for a theory, E always stands for some evidence here, that's warranted if T provides a better explanation of the evidence E than any available rival explanatory hypothesis. Okay, so the idea is you have some evidence E, and you have some available theories, T1, T2, T3, and so forth, and the one that provides the best explanation of the evidence is the one you should be inferring to. So you compare the theories in terms of how well they explain the evidence, you infer the best one. That's basically the basic idea here. Now, in order to apply that, we need to be told what it means for a theory to provide a better explanation than some other theory. And that's going to be the big issue in any account of inference to the best explanation. But I think philosophers tend to disagree a lot about what it is that makes for a better explanation. But one of the things the few things that I have agreed on, almost all of them, is that simplicity and explanatory scope are relevant. That's to say, a theory that is simpler than another makes it better, all things being equal, makes it a better explanation. And a theory that has a greater explanatory scope, that is to say, it's able to explain more of the evidence that you have, that also makes it a better explanation. Other explanatory virtues, in this sense, have been proposed, but I think those are by far the least controversial ones. Now, one important thing is that there's always a requirement of total evidence in the background here. This is a term that's from the mid-century, 20th century philosopher plus a rule of Carnot. The basic idea is that the evidence has to include all of the agent's relevant evidence. You can't sort of infer from just some subset of your evidence, some proper subset of your evidence to a theory. You need to infer from all of your evidence. So you need to include all of the evidence when you're evaluating the theory in terms of how good of an explanation it is. And the third point that's sort of not always recognized in this literature, but is that some inference to the best explanation can be sort of indirect in that you have some evidence E, you have some theory T, and then often what you do, you're not really inferring the theory T directly, but you're inferring something that follows from the theory. So you're inferring kind of a hypothesis of the theory, or something that follows from the theory, if you will. So it's indirect in the sense that it goes from the evidence to an explanatory theory to another theory that might not explain, actually, the thing you're inferring from, but it follows from something that does explain it. So that's the philosophical approach. And now, to get at the issue that I want to get at in this sort of framework, I want to start by asking the question of whether IBE, in this sense, licenses inferring that H1 is justified from the fact that there's expert consensus on H1. And for now, I'm going to be deliberately ignoring whether there's a disagreement, or the fact that there's a disagreement on H2 through HN. So let's just start with the question, does the consensus by itself warrant inferring that H1 is justified, the theory on which there's consensus? I think to see this, we can consider kind of two viable explanations of the fact that there's consensus on a given theory. They're going to be very salient to us, I think. I mean, one possible explanation for the fact that there's a consensus on a theory is that there's some sort of something I call a crowd psychology. So the idea here is that scientists just tend generally to form beliefs by following the lead of their peers or that of a scientific authority of some kind, irrespective of the scientific evidence. And H1 was believed by the expert's peers or by a scientific authority, and so that's why, according to this explanation, H1 there's now consensus on H1. I think this is a kind of explanation that I wouldn't espouse in many cases. But I think it's sort of something that has been proposed by some philosophers, some historians of science, some sociologists of science, as sort of a good explanation for a consensus on many scientific theories. Another kind of explanation you might give for any consensus on any theory is what I call critical evaluation. These are really forms of explanation. So that kind of explanation says that scientific experts form beliefs by examining the scientific evidence for a given hypothesis, at least somewhat critically and or independently of other experts. And H1 is overwhelmingly supported by the scientific evidence, and so that's why there's now a consensus on H1. Right. And so my point here is that if we're just considering the fact that there's a consensus on H1, and that's all the evidence we have relevant to this to the question of whether H1 is justified, it's very hard to see how you could choose between these two theories, or two explanations. It's very hard to see how you can have any reason to think that critical evaluation is more likely to be true than crowd psychology, or is a better explanation, or the other way around, if your evidence is just the fact that there's a consensus. Right? If you have no other evidence, right? So you're a non-expert and you're looking at the fact that there's a consensus, you know nothing about the community on which has reached a consensus, you really have no reason, I think, to prefer one of the explanations over the other. And so in that sense, there is no best explanation. There are two ones that are equally good. But the important part here is that in the cases we're concerned with, there's also the disagreement. That's the stuff that I asked you to ignore before, but now we're not going to ignore it anymore. So we're going to take that into account. There's disagreement on these other things, H2 through HM. And the point here is that, or the point that I want to make is that this discriminates actually between these two explanations. The reason is that crowd psychology, it wouldn't be able to explain why the experts would also have formed a consensus on these other theories. And so it wouldn't be able to explain that, and therefore it would suffer in explanatory power. There would be something you couldn't explain. Or it could actually, you could strengthen the crowd psychology explanation by adding some special reasons why they haven't formed a consensus from H2 to Hn. But then that explanation is going to suffer in simplicity. It's going to be a more complicated explanation because you've added stuff to it. So that's the idea. That's why I think crowd psychology would no longer be as good as critical evaluation when you add to the total evidence the fact that there's a disagreement on H2 to Hn. And now, since H1 is justified according to critical evaluation, that is to say, since H1 being justified follows from critical evaluation, this means that the disagreement on H2 to Hn helps support or provides a reason to prefer, or provides kind of a reason to think that H1 is justified. It makes one of the explanations according to which H1 is justified better than the other, which it wasn't before. So in that sense, it provides a reason, a positive potential reason. So that's the idea of how to spell out the basic idea in an explanations approach. And so turning then to a robustness approach, which is the last one I'll consider. So this is not really a very complicated idea. I mean, I call it so the kind of robustness analysis that I'm interested in is called inferential robustness analysis, which is a term I'm borrowing from James Woodward. There are other kinds of robustness analysis, and they work slightly differently each kind. But this one kind of works as follows. So suppose you have some data D, and you have some result R that you want to infer. But you can't infer R directly from the data D, because there's no entailment between the data and the result. Usually, it's not always the case in science. You don't have any deductive entailment from the data to your favorite theory, right? So the idea here behind inferential robustness analysis is that, well, you can make certain assumptions that would get you the result from the data. So take the data, add some assumptions, and you'll get the result. Now, there are going to be many different kinds of assumptions to be made, and the idea behind robustness analysis is that there's something special if a result can be obtained in that way, given any of the assumptions that you might want to make. So more formally, so you have some data D, and according to robustness analysis, the result R is inferentially robust given D, just in case a suitable set of competing assumptions, A1 through AK, which are about R in some sense, D implies R given any such assumption. So whatever assumption you make, you'll get the result R given D. Now, in the ideal case, you want the set of assumptions to be such that you know that at least one of them is true. In that case, you can be absolutely certain that the data D entails the result R. But that's a really, really unrealistic case. In fact, if you do have that kind of case, you don't, it's not, this is sort of, at this point we're talking about the deductive kind of inference. It's an inference that's guaranteed to be true, so it's not really of the kind that is, well, really ever relevant in science. Right, yeah, it's proof by elimination of cases, really. So if you do have a complete set of assumptions in this sense, you're not really talking about sort of empirical confirmation in the usual sense of that term. So that's a very unrealistic situation. It's the ideal situation, but it's a very unrealistic one. So the more realistic situation is that you have some assumptions, and you have some assumptions that are kind of sufficiently diverse, they're sufficiently different, each of the assumptions, to somehow reflect a sort of spread of plausible possibilities, or about how the thing that you're trying to model, get a result about, is. So you have some diversity in the assumptions that you make. So that's the sort of more realistic, good case. Not ideal, but still very good. And so this is meant to, the idea behind inferential robustness analysis then is that this is meant to prevent the result R from being sort of artifact of any of the specifics of the given assumptions that you make. And this indicates that R really holds given that D holds. So now applying this to the case at hand, again, we're going to be using terms like data and results slightly unusually, because the data for us are going to be not so much the scientific data, but the fact that someone says something, or the fact that there's a disagreement or a consensus about something. So the data in this case is going to be the fact that there's a consensus on H1. The desired result is going to be the claim that H1 is justified. And the assumptions, each assumption, which I'll call A, E, I, represents the possibility that expert EI's attitudes are epistemically justified. So then we have that for all of these assumptions, for each of these assumptions, the assumption together with the fact that there's consensus entails that H1 is justified, since according to the assumption that that expert's attitudes are all epistemically justified, and according to the consensus on H1, that expert, of course, and all the other experts, of course, are too, they do think that H1 is true, and so they together entail that that H1 is justified. Now, although these assumptions, of course, are not complete, the fact that there's disagreement on H2 through Hn indicates that it is a diverse set of assumptions. After all, the fact that the experts disagree on a variety of other hypotheses surely suggests that they respond to evidence differently, for example, due to different background beliefs, or different methodologies, or different, maybe different data sets, whatever it is. So another way to, I think, more kind of colloquial, more intuitive way to think about it is as follows. So the disagreement about H2 through Hn, which are these claims that there's disagreement about, that indicates that the experts have a variety of ways of responding to a given evidence set that they might obtain. On the other hand, the consensus on H1 indicates that H1 is justified according to any of these ways of evaluating the evidence, any of these different ways of evaluating the evidence that the experts have, or that they operate. And so together, this suggests that the justification of H1 is robust in the sense of the sense used in inferential robustness analysis. And so therefore, if inferential robustness analysis is a good methodology, then H1 is indeed justified. And the essential point here is that the disagreement on H2 through Hn is really important. Because we wouldn't really have reasons to think that H1 is justified. The fact that H1 is justified is robust, or so the claim that H1 is justified is robust, if the experts also agreed on H2 through Hn. Okay. I think I'll just skip this objection that I have in the longer version of the paper, and just summarize so we have more time to talk. So for questions. So the summary is just I've sort of considered 3 ways of showing that expert disagreement can be a reason to trust the consensus. So on the Bayesian approach, the probability that a consensus hypothesis is justified is raised by the disagreement on other hypotheses, I think, given a possible assumption about the probabilities. On the explanations approach, the disagreement makes critical evaluation a better explanation of the total evidence than crowd psychology, and so therefore, because the hypothesis being justified follows from the former but not the latter, it gives us a reason in that sense to trust the consensus. And on the robustness approach, disagreement indicates epistemic variety among the experts, and so also indicates that the hypothesis being justified is a robust result in a sense, in a relative sense. Okay, thanks.